So hello everyone. Today we have another learn and share session. This time with Tohru from Aztec. Tohru is basically going to explain Zeromorph, which is his latest paper, if I'm not mistaken, which is basically based on some kind of isomorphism, to put it in some sense, in between the multivariate and the univariate world. But I guess he will definitely explain it better than me. So thank you for coming, Tohru, and please feel free to start.
Thank you, Carlos, for introduction and invitation to give a talk here. And thank you everyone for coming. So I'm going to talk about Zeromorph. This is a commitment scheme, and the work is a joint work with Patrick. We are working at Aztec. So let's jump in. First, I'd like to get it out, what a Zeromorph is. So Zeromorph is a recipe. It's a generic construction recipe to convert additive univariate PCS with degree check into a multilinear PCS. I'm going to explain what this degree check and etc. later, but for the moment, please keep in mind it's a recipe, it's a generic construction. Okay, so the plan of the talk is this. First, I explain the background of the research, and then step back a bit and talk about the PCS in general, then introduce our core concept, main concept called univariatization. And after that, we explain the evaluation protocol. And up until this point, everything is a generic construction. This is about the recipe part. And after this recipe part, we explain how to instantiate this generic recipe with univariate KZG univariate commitment scheme, using it as an underlying commitment scheme. And that's the second half of the talk. And finally, if we have time, I will mention the shift evaluation, which is an important kind of useful primitive for SNARK, for application in SNARK proofs. Okay, so the background. The background is the subject-based proof of circuit satisfiability. This is what we are trying to do and what we want to do right now at Aztec. And we start with this Plonk arithmetization. What I'm going to say in this slide applies also to like R1CS, other algebraic arithmetization. But for the moment, I have Plonk in mind. Start with it, and usually Plonk, we prover encodes witnesses, that is the wire values, as by using this univariate Lagrange interpolation. But this approach is a bit different. We encode the witnesses by multilinear extension. So to do this, what we do is this: we have the wire values of witnesses, and then prover place them over the Boolean hypercube, hypercube, and then take the multilinear extension of it. And it is known that there is a unique multilinear polynomial that extends the witness values placed over the Boolean hypercube. And after making these witness polynomials, making the proof, the verifier needs to check the constraint, for example, the gate constraint. And this constraint check is run by subject protocol. And this part is there is a standard trick. We think of the constraint. Constraint check is basically you have a polynomial, a constraint polynomial, and you plug in the witness values in it and see if the value is 0 or not. So to use the subject, what we do is we take the random linear combination of the constraints, and then we evaluate this, randomize the sum of the constraint using a subject protocol. At the end of the subject protocol, the verifier needs to evaluate the polynomials on which the subject protocol was performed. And in this context, this polynomial is the witness polynomials, which are committed. And here comes the evaluation protocol. And this is where we need a multilinear evaluation protocol. And for this purpose, we want something efficient and we want it to be zk.
It's radical, like, I love the cause, but I agree. It's like one.
I'm sorry?
Yeah, it's not enough. It's not always very good at it.
Okay, so we need a, was that a question or?
No, I
No,
just think
I-
that we
Someone
can
was unmuted, but is muted already. Apologies.
Okay, no. Okay, so here we need efficient zk multilinear evaluation. And by efficient, we mean, like, of course, the prover needs to be efficient, verifier needs to be efficient. But when we talk about the efficiency, we should also keep in mind this the cost of random nonces. The generating the random nonces to endow zk property is also it's also a matter to consider. So Zeromorph is take care of this kind of aspect as well. But so before talking about the Zeromorph, let's step back a little bit and then talk about the polynomial commitment schemes in general. So I think this is kind of already familiar to many people, so we do it quickly. But PCS consists of algorithms setup that takes the security parameter and output public parameters, which is used in this commitment and open protocols. The commitment algorithm takes the polynomial as input and then also public parameter as input and output commitment element. Oftentimes it's a group element. And the open protocol is the protocol that takes the commitment element and then polynomial revealed by the prover. And then verifier can check if the polynomial claimed to be, polynomial is consistent with the commitment. So this first three is just the usual commitment scheme. The polynomial commitment scheme, the crucial part is the next one more protocol built on top of the three. This final one, evaluation protocol. The purpose of the evaluation protocol is this. So verifier has a commitment, and then he doesn't have the polynomial itself, but verifier chooses a random point and asks the prover to give the evaluation of the committed polynomial. And evaluation protocol allows the verifier to check if the claimed evaluation is indeed the correct evaluation of the committed polynomial. And this evaluation protocol it's technically, this is a protocol that allows the verifier to check a certain polynomial identity. And yeah. So let's look at this polynomial identity, example of the polynomial identity. And this is the multilinear, we are going to talk about multilinear KZG polynomial identity here. And which I chose this as an example because this is very important and for Zeromorph construction. And in fact, Zeromorph is based on this idea. So F is the commitment polynomial, and then here the bold F is the finite field, and this superscript less than 1 denotes like multilinear, meaning that F is a polynomial of degree 1 in each variable. Okay, and U0 to UN minus 1 is a point in Fn, and this is the point the evaluation is carried out. So so F evaluates to V. This first equation is equivalent to the second one. The existence of Qi, this is a Qi, the polynomials, such that this equation, the last equation, holds. So if you think of the n equals 1 case, that is the one variable case, the usual univariate KZG, the left-hand side becomes just the x0 minus u0 times q0. So the statement is F evaluates to V if and only if F minus V is divisible by x0 minus u0. And in this univariate case, what the verifier's job is to make sure that this equality holds. And what happens is prover commits to F initially, So that's okay. What prover provides the commitment to QI to a verifier, and verifier checks this equality using elliptical pairing. For this multilinear case as well, there is a multilinear SRS, which is just a little different SRS from the univariate case. For the multilinear case, again, the prover provides the commitment to QI, multilinear commitment to QI, to a verifier. And then verifier checks the equality using elliptical pairing. But this pairing, as we know, it's a kind of, so pairing replaces one dot, this multiplication on the left-hand side. So if you follow this approach, when you have more than one variable, you need to carry as many as n pairing computations on the left-hand side, and plus one for the right-hand side. So if you use the traditional approach, incurs many pairing computations. And if it's possible, we want to avoid it. And in the market, we just look around the market, and we have these Virgo and Gemini multilinear protocols, commitment schemes. They are based on univariate evaluation protocol. So their evaluation protocol is based on the univariate evaluation protocol. And univariate evaluation, so the idea is, can we do something like this to avoid many pairing computations? That was the initial conception of Zeromorph. And so, for example, like, this is what we are going to, so can we apply some of the ideas to Virgos and Gemini? And at the very conceptual level, Virgo and Gemini's really fundamental idea is to convert multilinear polynomials into univariate polynomials. So when we look at it, this last map, this is a map from the vector space of n-variate multilinear polynomial to the univariate vector space of univariate polynomial of degree less than 2 to the n. Do we have some nice map that can be applied to equation 2, so that equation 2 itself will be converted into a univariate equation? That means this is a multilinear evaluation protocol in where verifier needs to evaluate only univariate polynomial identity. Well, that's how it started. So the main part is first main task is to construct a nice map like this, which we call univariatization map. But perhaps at this point, I think some people are already thinking that why don't we just use Gemini, because Gemini is reasonably efficient. And my answer, well, it's not really an answer or problem or anything, but the first stumbling block for us was the ZK property of Gemini. It is possible to add ZK property to Gemini by using a standard technique of standard technique, by which I mean, like, you choose a hiding polynomial as big as the commitment polynomial. So in our case, the commitment polynomial has 2 to the n, the first line, 2 to the n coefficients. Okay, if we use the generic ZK technique, then we need to generate 2 to the n number of random nonces. And that's a bit too much, and we just hope to avoid it. And the second point is, this is a minor issue maybe, but this Gemini requires univariate evaluation at different points during the evaluation protocol. And evaluating polynomials at different evaluation points generally is well, more difficult than batching different polynomials and open them at one point. So if we can avoid it, it's very nice. And Zeromorph does both of them. So Zeromorph uses only logarithmic number of nonces for ZK property, and Zeromorph opens the univariate polynomials only at one point. Okay, okay. So now let's talk about the univariatization map whose purpose is to convert multilinear KZG polynomial identity into a univariate one, which is possible to check the identity. So we need to choose the right one, something useful for us. And our answer, the suitable univariatization map for us, is the following. I explained this with a bivariate case first, because it's much easier to look at. So when you have only two variables, our answer, the univariatization map, is this. You have bivariate multilinear polynomial f, and that is sent to a univariate polynomial whose coefficients are evaluation of f over Boolean cubes. And the way we place this evaluation is very simple. So we interpret these red letters as binary representation of integers. So like 0, 0 represents integer 0. Therefore, it is placed at degree 0 term. And 1, 0 represents integer 1. For us, the left is the least significant bits. So 1, 0 is a binary representation of 1. Therefore, it is placed as a coefficient of degree 1 term. And 0, 1 represents 2. So it is the coefficient of the degree 2 term. And 1, 1 is 3. Therefore, it's the cubic term. Now first, let's observe one thing. F is, okay, I said F is a linear isomorphism, but this is wrong. What I want to say is that the map written here is a linear isomorphism. I'm very sorry about this. So this univariatization map is a linear isomorphism. As you can see, this is obviously additive in F, and this respects the scalar multiplications. And now this is an isomorphism. Now look at the target and the source. Both of the vector spaces, both vector spaces have dimension 4. So to show that this is an isomorphism, we only need to say it's an injection. So let's look at the kernel. Say that this f of 0, x0, x1 is mapped to 0 polynomial. That means all the coefficients are 0. That means f evaluates to 0 over Boolean cube. But the evaluation of a Boolean cube uniquely characterizes the multilinear polynomial. That means f itself is a 0 bivariate polynomial. So this is injective, therefore isomorphism. And now, and one more thing, this is slightly not about the univariatization map itself, but if we want to use this commitment scheme for snark provers, then a snark prover starts with the witness polynomial. Yeah. So they place the witnesses over Boolean hypercube, hypersquare, hypercube, and then extend it, right? So for this kind of prover, the univariatization is free because he already starts with the evaluation of f over Boolean hypercube. These are the coefficients of the univariate polynomial are just the witnesses they start with. And this property and this construction of the map naturally generalizes to n-variate case. So here, f is mapped to u of f, and we give the name u to signify univariatization. F is mapped to u of f, the polynomial, univariate polynomial whose coefficients are evaluation of f over Boolean hypercube, and the coefficients are placed according to their degree. They are placed in the proper degree place. So b0 to bn minus 1, interpret this as an integer, and then place it in this degree. Okay. Now, one easy example is the constant polynomial. For v in the field f, and we see this as an n-variate polynomial. In this case, u of v is the polynomial written here. All the coefficients of v, because it's a constant polynomial. So they evaluate v at every Boolean hypercube, Boolean points. And we are going to use this u of v later in this talk. So, yeah. And to commit to multilinear polynomial f, a zeromorph prover commits to the univariatization u of f using a univariate commitment scheme. So, for any questions? Okay. So now we just settled how to convert multilinear polynomial into a univariate polynomial. Now let's talk about the evaluation protocol. We start with the KZG multilinear polynomial identity that we saw earlier today. So f evaluates to v if and only if there exists qi, such that equation holds. But now I placed a variable condition here. X0 qi depends only, qi is a polynomial only in the first I variables. This is the condition I placed here, and then the claim is even with this condition, this equivalence is true. And now this condition will be used in the zeromorph construction, and this will be the point where that verifier needs to verify. So anyways, so we're not going to check this final equality with pairings. What we are going to do is, of course, apply the univariatization on both sides. And so the final one, what is this equation? Equation 5 is the polynomial identity we obtain. Okay, to check it, so the idea is verifier can check this equation 5 at the random point, invoking to Schwarz and Sippel argument. Now, the univariate commitment to u of f is given as an initial commitment to f, okay? And suppose the prover gives the commitment to u of qi as an evaluation proof. Then the verifier can evaluate u of f and also u of qi at the random point. And verifier can also compute u of v at random point because u of v has this nice form, as we saw in the example before. So if the verifier can evaluate u of xi qi, then the job is done because everything can, yeah. So can we do that? And if possible, we want to do it with the commitment to u of qi without asking prover to commit u of xi qi for the cost reasons. And then luckily, if the qi satisfies these variable conditions, under this condition, we can do that. So this one, the fact is u of xi qi is a product of this fraction and u of qi if qi is a polynomial in the first I variables. So obviously, if you can evaluate u of qi, then you can evaluate u of xi qi. Throwing this in, we obtain this polynomial identity. F evaluates v if and only if there are qi with this variable condition such that the final equation holds. So the verifier, upon giving the commitment to u of qi, verifier can evaluate both sides using a univariate evaluation protocol. Now, the extra task for the verifier is he needs to make sure that qi satisfies these variable conditions. And luckily, there's a way to do it. And it depends on this fact. qi belongs to this honest space, satisfies the variable conditions. It's a polynomial in the first I variables, if and only if there is Ri of bounded degree at most 2 to the I, such that U of Qi is Ri times Vi. And Vi is the polynomial of this nice form. So the idea is this: instead of asking prover to commit, making prover to commit to UI, U of Qi, we make them commit, make the prover to commit to Ri. Then that should do the job. But before, yeah, let's pause a little bit and then look at the meaning of this fact. So this fact actually means that if Qi satisfies the variable conditions, the coefficient of U of Qi is periodic. In fact, if you write U of Qi equals Rivi in a more explicit way, I mean, if you write the Vi in an explicit manner, you get this U of Qi is Ri x plus da da da. And this, because Ri has a degree less than 2 to the I, this simply says that the coefficient of U of Qi is a repetition of the coefficient of Ri. In fact, we even know that Ri is a truncation of U of Qi. It's just a degree less than 2 to the I part of U of Qi. But then maybe it helps an example here. So suppose n equals 3. N is a number of variables, so 3 variables. And Q2, okay, it should depend on the first 2 variables. So Q2 is the 2, for example, 2x0 plus 1x1. In this case, you can compute U of Q2 like this. Remember that coefficients are just evaluation of Q2 over Boolean cube. So if you evaluate them and if you place them, you get something like this. Indeed, repetition. It repeats because Q2 doesn't have x2 inside. So regardless the value of x2, Q2 take the same evaluation. That's why this repetition happens. In any case, we can write it in this product form, just as the fact says. Okay. So I just erased the meaning and example. The fact is there. And our previous polynomial identity was this. And we use the fact to replace Qi and U of Qi with Ri. Okay? And remember that Ri needs to satisfy degree condition. Ri needs to be less than 2 to the I. And so now we get, using the fact, f evaluates to V if and only if there are Ri which are of degree less than 2 to the I, and in fact, yeah, such that the last equation holds. So now this degree is something verifier needs to make sure, needs to check later. Okay, so this last equation can be written in a slightly better way, or like just better looking way, because Vi, if Vi can be divided by this denominator x to the 2 to the I plus 1. And this is easy to see from the fraction form definition of Vi written above. Indeed, Vi divided by the denominator is just a Vi plus 1. So you get the last equation. So, yeah, so this is the Zeromorph's polynomial identity. So basically, prover commits to Ri of x as an evaluation proof, and verifier evaluates the last equation at the random point. Using univariate evaluation protocol, verifier can evaluate Ri and U of f. U of v, he can evaluate it himself. And this big chunk in the parentheses right after the summation are all public polynomials. So this can be done by the verifier. So let's write down the evaluation protocol. So I just transcribed the last polynomial identity here on top. So first, the prover computes Ri. Ri was just a truncation of U of Qi. So he puts Ri like this and output the univariate commitment to it. And I goes from 0 to n minus 1. And PMV, prover and verifier, engage in a degree check protocol, which we assume that the commitment scheme allows. Degree check protocol to check degree of Ri is indeed correct, and then degree of U of F is less than 2 to the n. This last part, I didn't explain this. Degree of U of F is less than 2 to the n. This is a technical point. We needed this to show the extractability of the scheme in standard model. And that's why it's there, but it's a technical point. So, and after this, the verifier chooses a random point, alpha, and this is the point where this polynomial identity is going to be checked. And after that, PMV engage in the univariate evaluation protocol to verify this capital F takes a value 0 at x equals alpha. So what is this? Let's look at this. First, we assume we need the commitment scheme to be additive. And the commitment to U of F is given U of F, and Ri are given to the verifier. So verifier can simulate the commitment to F of X because this chunk, the parenthesis after the summation, is already evaluated at R alpha. And checking that capital F of X takes value 0 at x equals alpha is precisely this polynomial identity equation written on top of this slide takes, they hold at x equals alpha because the f of x, the capital F of X is the right-hand side minus left-hand side, partially evaluated. And this is a scheme. And now one property, this is a property, is if the univariate commitment scheme is hiding in ZK, and the degree check used in the second step is ZK, then the zeromorph evaluation is ZK. Maybe we can look at this one by one. Because the first part, step 1, the transcript is the output commitment. If the commitment is hiding, this is uniformly distributed, you can simulate that. And second point is a degree check. And all the transcript in the second point is internal to the degree check protocol. So by assumption, if degree check is also ZK, that's an assumption. This can be, all the transcript can be simulated. Third point is a public coin. Okay, you can simulate that. And the fourth point is the evaluation protocol. And the evaluation is always 0. This is not a message. So all the transcript is internal to the univariate evaluation protocol. Again, this is ZK by assumption, so you can simulate that. So this is all about the recipe. And we instantiate this. To do that, we use a hiding KZG commitment. Hiding KZG commitment is like a tweak of the KZG commitment in the style of Pedersen commitment. And yeah, so we make the KZG commitment hiding, and hiding, okay? And then we also make a degree check protocol for hiding KZG commitment scheme, commitment element. And I'm going to explain this now for the rest of this talk. But is there any questions by now?
There's nothing in the chat either, so not for now, it
Okay.
seems.
Cool. Okay. So yeah, so for the rest of the talk, I'm explaining this. And logical way is, of course, we have to first we define the commitment, and then define the hiding commitment, and then define the degree check on top of it. But that's kind of messy. So I want to explain the principles. So what I'm going to do is this. I'm going to explain the degree check protocol for ordinary KZG commitment. Okay. I do it for the ordinary KZG commitment. And after that, I will explain how to add hiding property to it. And modification is straightforward. So now we do the batched degree check protocol. Why suddenly batched? Because in the second step here, we need to perform degree check for multiple RIs and multiple degree bound 2 to the I. So it's nicer to have a batched protocol, and we are going to make it. And there are two steps to do it. The first step is the degree bound KZG evaluation. So this is a building block. And what this protocol does is allows simultaneous evaluation and degree check of a single polynomial. Okay. And the second step is the batching technique. And this is the technique to reduce multiple degree checks to a single degree bound KZG evaluation. That is the first scheme. So multiple degree check is reduced to a single, not to a single degree check, but single degree bound KZG evaluation. So this evaluation is an additional part. But then, yeah, so I will do it one by one. So degree bound KZG evaluation. This is inspired or hinted by Sonic paper, and the scheme is very similar. Small difference though. So let's denote Nmax. By Nmax, we mean the strict upper bound of degrees of commitment polynomials. We are talking about ordinary KZG commitment scheme here. So this means that the KZG prover key is the ordinary notation. G1 is the generator of the first group, and tau is the trapdoor. And the SRS goes up to tau to the power of Nmax minus 1. And the goal of this scheme, degree bound KZG evaluation, is to evaluate F. This is a univariate polynomial. For the rest of the talk, we talk about this underlying univariate schemes. So yeah, so probably until very last moment, F is going to be a univariate polynomial from now on. To evaluate F, takes the value V at U and check that the degree of F is less than some prescribed specific integer D. And the scheme I'm going to talk about here works only for non-zero evaluation point. Okay, the idea is simple, is to just multiply both sides of the KZG polynomial identity by x to the power of Nmax minus D. So what happens is this. Prover computes the ordinary KZG evaluation proof polynomial, quotient polynomial Q of x, and he raises the degree of Q of x to the by multiplying x, this blue part, and he commits to it. And verifier check the equality of this identity using a elliptic pairing. But to deal with the right side, the very far right element, x to the power n max minus d, and verifier needs a higher G2 verification key. But the idea is this. So if why is this enough? Let me explain why this is enough. So if the commitment polynomial f has degree greater than d, some illegal degree greater than d, then this quotient polynomial Q has degree at least d. And now this blue part has degree at least and max, which because of the length of the SRS, prover cannot commit to. So the fact that prover committed to something already says that the polynomial has a, committed to something already says that the Q of X or the committed polynomial has a proper degree, n minus max minus 1. And now that's how to assure the degree part. And this the evaluation part is assured by this. If this polynomial equality holds, then x minus u divides fx minus v. Then that means, of course, f of u is equals to v. Now, if u equals 0, then x minus u becomes x. So it may not necessarily divide fx minus v. It can divide this higher v key part. Then the scheme fails. So that's the idea. But in any case, the protocol goes like this. Prover commits to this blue part and verifier checks like pairing and is using higher G2 verifier key. So this is the modification we need to make to the SRS, the red part. Okay. So now we are going to
one question, Tohru. So you are now relying also on the speed, more at least on the speed of G2 operations. Is that correct?
I'm sorry?
Are you relying now more when applying Zeromorph on the speed of G2 operations, or I just misunderstood the thing?
So we changed the verifier SRS to include tau and max.
Oh, fair enough.
V.
Okay.
Yeah.
Okay. Thank you.
Okay. Thank you. Okay. So this is the degree bound case G. Yeah. In particular, this allows the degree check of a polynomial. Okay. Okay. Next one, we are going to talk about the batched degree check protocol. And the goal is to check a multiple degree bound like this, degree fi less than or equal to di. If all the degree bounds are the same, then it's much easier because what you need to do is to take the random linear combination of fi, that is yi, what's written over here in this big bracket. You take this random linear combination and then just run the degree check on this single polynomial. Because if one of the fi has, illegal degree, big degree, this coefficient will rarely be canceled out by random linear combination. So with this idea, this is a simple idea, but maybe we can use this for a general case where degree bounds are different. The idea is to raise the degree of fi, all of them, to the same level by multiplying the power of x. So this is what we're going to do. Choose d star, which is bigger than any of di or equal to di, and check the degree of this random linear combination. If this random linear combination has degree less than d star, then red part has degree less than d star. Therefore, the fi has degree less than or equal, less than or equal to di, right? But to do something like this, it's not a proper protocol yet, it's just an idea, but to do something like this, we need prover to commit to this red part. Then we need to make sure that this red part is consistent with the commitment to fi. And this can be done, for example, by this method. Just choose a random small x and check the difference, this red part minus partially evaluated red part evaluates to 0 at x equals small x. Then this is just an idea, and then we combine them together. The solution is this. Set zeta sub x. This is a polynomial. And we have this blue part, which we see above. Yeah, we also have this above, blue part. And then take the difference of blue part and partially evaluated blue part. And we make the prover to commit to this blue part, which we call f of x. And run the degree bound KZG to check zeta xx has degree less than d star plus 1, and zeta xx is 0. So let's say why this is enough. First, by checking the degree of zeta x is less than d star plus 1, we know that the blue part, that is the f of x, has degree less than d star plus 1. And this implies that the degree of fi is less than or equal to di. And here we are actually regarding this zeta x of x as a linear combination by this small x. So that this blue part contains no small x, and the second part of the zeta x equation contains small x. And we think of this as a randomization, random linear combination by small x. So if you see it from this point of view, then the degree of zeta x is less than d star plus 1 implies that the blue part has degree less than d star plus 1. So that assures the degree bound of fi. But then we need to make sure that this claimed commitment to blue part was indeed honestly computed. And to make sure that this is honestly computed, this part is done by this evaluation, evaluating zeta x at x equals x, small x, and show that it becomes 0 is enough to ensure that the commitment to blue part is indeed correctly formed. Yeah, it turned out it was enough. Okay. So let's write down the protocol. It's getting a little bit confusing, I'm afraid. But okay, so here the notation is the same as before, and the protocol goes like this. Verifier chooses random y. Prover chooses commitment to, no, prover commits to this first part, the f of x. Verifier chooses x. This is the evaluation point. And prover and verifier engage in the degree bound KZG. And this protocol, this degree check protocol is ZK. This is a property we needed for Zeromorph to be ZK. And why is this ZK? Let's go one by one. Step 1, the Y is random, simulatable. 2, this can be simulated by the simulator because simulator has commitment to look at the definition of fx. Simulator has commitment to fi, and y is already simulated. And what is this? X, this power part, x to the power of d star minus di plus 1, this takes just a trapdoor, and simulator is allowed to use it. Therefore, step 2 is simulatable, and step 3 is an independent random nonce, and step 4, this is degree bound KZG. And degree bound KZG is actually just like ordinary KZG, transcripts are deterministic to the input. So everything is simulatable here. So what we need, we got the ZK degree check protocol, and we have the KZG commitment scheme. Then we need a hiding KZG. So the hiding property is what is missing. to instantiate the ZK zeromorph now. And here's how to make the hiding property as the hiding property. So this is a particular special case of the VC-code paper. And the idea is from, I think, idea is the same as the Peterson commitment. And while working on this, we found that the proof in the VC-code paper wasn't exactly correct. So we corrected that and gave the new proof in our paper. So the idea is randomize KZG commitment with a second trapdoor. Simply add second trapdoor to the prover key and verifier key. So to commit, by the way, I'm focusing on the commitment part only. And so I temporarily forget about the degree check. So I didn't include the higher G2 powers here. So just look at the ordinary KZG and make it into a randomized hiding KZG. And for the hiding KZG, the prover commits to, when prover commits to F, prover computes the ordinary commitment, F tau 1, and then randomize it with the second trapdoor by choosing a nonce R. And to evaluate, for the evaluation protocol, prover provides the ordinary, computes the ordinary KZG evaluation quotient polynomial QX and commits to it, and then randomize the commitment with a random nonce S. And now to verify, of course, these two, C and pi, are not enough for the verifier to verify anything because R and S are completely independent. So we need an error term. Prover, knowing S and R, both of them, the prover can compute this error term. What verifier does is the usual KZG pairing check with the error term. And error term just adjusts the difference. And this is still ZK. This is now randomized. So this is a hiding KZG. And we might be afraid that we might have lost that ZK property here, but it's not the case. It's a bit, why is that? Because first, the transcript is pi. Pi is completely random. So the simulator can simulate this. And what about delta? Because delta depends on R. Oh, but then it's fine because when in the honest prover case, when the pairing check passed, pairing equality exactly means that tau minus u pi equals C minus V minus xi delta. And verifier has all the access to all of them. So verifier knows, no, I'm sorry, the simulator knows the tau, u, pi, c, v, xi, all of them. So simulator can compute delta. So this is ZK. Yeah, so let's talk about the cost evaluation of this scheme. When the zeromorph is instantiated with the hiding and ZK KZG, and if we perform a little bit of optimization, we get this cost. And capital N is the number of coefficient. Okay. The prover cost. Oh, and I didn't include the field operations in this cost, but that is, yeah, field operations are linear in N, I mean in capital N, with small coefficient. So we ignore it. Prover cost is G1 MSM of total size 2. And this is the cost of evaluation protocol. I don't include the commitment phase here. So prover cost is a G1 MSM, the first elliptic curve group MSM of total size 2.5n plus 1. And by this total size, I mean, this is a MSM of not one polynomial, but several polynomials. And total size means the total number of coefficients. Verifier cost is the G1 MSM of total size 2 log n plus 2. Oh, maybe I should say one more thing. So proof of course is this, most of this thing, the G1 MSM comes from the commitments to I's, and what is this? The commitment produced during the evaluation protocol. Commitment for the KZG evaluation proof. Those account for this 2.5n of the proof of cost. And verifier cost is, just a 2 log n plus 2 and 2 G2 operations, 3 pairings. And proof size is log n plus 3 G1 elements. These are mostly commitments to RIs. And log n plus 2 proof annonces. And this is all for hiding KZG commitments. So for the ZK property, we use only log n plus 2 nonces. And 3 verifier nonces. And the protocol is constant 5 rounds. That's the cost. Any questions?
Yeah, can you oh, sorry, go on.
I was gonna ask, where does the 0.5, like which polynomial is 0.5 in length?
Oh yes, this is the degree check polynomial. So there was this point. Oh yes, so this f polynomial here, we commit to f. Now for us, this fi are the ri's, and the maximum degree of ri we have is n over 2. So we actually have n over 2 coefficient to commit to fx in the application has n over 2 coefficients. That's where the 0.5 comes. Okay.
Got it. Thanks.
Thank you. Yep. So now, well, we don't really have so much time, but let me just advertise a little bit about the shift evaluation, even though it's going to be a very sketchy explanation, but just tell you what feature we have. And if you have
Don't
question,
worry, don't worry about time. I think we're all fine. So just take all the time it needs you to explain it as well as you want.
Thank you. So shift evaluation is not really about the polynomial commitment scheme. It's about the polynomial commitment scheme, but it's something interesting for snark applications, especially when you need to do something like a lookup protocol or permutation argument. And here is what it is. F is the polynomial. This is the witness polynomial. Okay. And say the witness polynomial has the form. Okay, F is a witness polynomial such that its univariatization is of this form. So A0, A1, A2, these are evaluation of witness polynomials over Boolean hypercube. That means, by definition, A0, A1, A2, these things are witnesses. Now the shift of the witness polynomial, shift of F, is defined as the polynomial, such that the U of F shift is this guy. The coefficient is shifted 1 down. You see, A0 became A1, A1 became A2, So this guy, in meaning, the shift polynomial F shift is a polynomial evaluates to witnesses shifted a little bit differently here. So the witness placed on the origin is now A1 instead of A0, like F. For witness placed in the position 1 is A2. and position 2 is A3. So if you picture it as a, for example, like the execution, think of witness as an execution trace of a circuit, then this F is a polynomial corresponding to the column that starts with A0 and then goes down A0, A1, A2, A3, da, da, da. And F shift corresponds to the column that starts with A1 and A2 and A3. So it's shifted one up, okay? And in the lookup protocol or permutation argument, the consistency check ranges over 2 rows of this column. So it's nice to be able to open both F and F shift with one commitment. So it's about the application thing. But if I formulate, say it in one word, our goal is this. With the commitment to F of U, not F of U shift, evaluate F of shift. And the short answer is yes, we can do it if at least if A0 is 0. When A0 is 0, there is a nice form. XU shift is UF. So we can do, by leveraging this, we can do this. Just a short answer. And one more thing I want to mention is the batch evaluation. This Zeromorph comes with a nice batch evaluation. So you can batch multiple standard and shift evaluations at a single common evaluation point. And this is what we need in practice. So the single point evaluation is already interesting in practice. And so it's very nice. And when we do this batching, the prover only needs to work with a batched polynomial. So prover's main task is to compute Ri, the evaluation proof, and commit to them. But prover can first batch the polynomials and compute Ri for this single polynomial. So he doesn't need to do multiple works and then batch or anything like that. He can batch first and compute Ri in one go. Yeah, that's the feature of Zeromorph. And yeah, this is the end of my talk. Thank you.
Thank you very much, Tohru, for the talk. If you have time, maybe there's questions. So then
Yeah.
we can, if you accept, maybe there's one in the chat. If you want to read it out loud.
Excuse me? Hello?
Yeah,
Can you
hello.
hear me?
Yeah,
Patrick,
Francois, yeah, go on.
So perhaps I just wanted to add something, perhaps that should be stressed a bit. It's mainly about the costs of Zeromorph. So one key property here is really that you can get zero knowledge with only log n randomness. And you have to think about it, what n is in practice. So n is like 1 million, so 2 to the 20 in practice. And if you had to generate like 1 million random field elements in practice, means you first have to run, a PRNG on your software, on your hardware. Then you have eventually to make sure that from these random bits, you have to get an integer that is really between 0 and the size of the field -1, and make sure that the distribution is very close to uniform. So you can use several techniques like reduced sampling and everything. But the point is that doing that in practice actually is very expensive. You usually, if you do it 1 million times. So Zeromorph is really, at least to the best of knowledge, the first proof system that achieves, zero knowledge, which only log n randomness, while maintaining all the other aspects, all the computational aspects, to the best that we currently have. In particular, also having only constant number of pairing computations to do for the verifier. That's just one main point I wanted to stress about Zeromorph. And yes, I will let Tohru answer the other questions in the chat.
Thank you, Patrick. That was really insightful. I will read it out loud so that we have it for the recording. Can you summarize the changes in the universal setup? A standard ECG setup. How does the number of G1 or G2 elements change?
Okay. Yeah, that's a good question. Yeah. So G1 stays the same. No, G1, we need to include, what is this? The second trapdoor. What's going on with my screen? Okay, for G1, we need to include this Gzai1. For G2, we also need to include Gzai2. And we need to include this higher G2 power we talked about here. And in the zeromorph scheme, the degree check we perform is of the form 2 to the I. Degree bound is always 2 to the I for zeromorph. So what we need is the tau, the higher Z2 element of the form tau n max minus 2 to the I. So that means a logarithmic number of G2 elements. Does that answer your question?
Yeah,
Thank you.
he said yes.
Yes,
Yeah.
thanks.
Thank you.
The subsidiary question is what if you're in a deployment that does not care about the hiding property, but you're running through the slides and highlighting those elements kind of gives the answer, right? So there's elements you need for the degree bound and then elements you need for the hiding property.
Mm-hmm. Yeah, yes. So two elements, yeah. For hiding property and degree check property.
I do have two questions. One of them is kind of related to that, which is if the underlying scheme that you use, like, I don't know, Plonk or whatever, is simulation extractable, using Zeromorph on the top breaks the simulation extractability property or not?
The question is, if I use this scheme for Plonk arithmetization,
Yeah.
can I still simulate the transcript and everything? Is that a question?
So
I think what he means is that you can still extract, basically from a prover, you can
exactly.
extract even if he has seen, even if the prover has seen simulated proofs before.
Exactly.
We haven't really thought about simulation extractability yet, but since what is at the heart is really just KZG, if Plonk manages it, I don't see why this wouldn't work as well. But I don't want to commit on any answer there because we just haven't thought about simulation extractability in depth.
Fair enough. And the second question is in line to what you said, Patrick, about generating like millions of field elements of randomness. So just to see if I follow your idea, the motivation for this work is basically the fact that you needed a way to basically be able to prove within Plonkish arithmetization or whatever big amounts of let's say statements that require big amounts of pairings. So you actually needed a way to reduce the amount of pairings needed to prove and verify these interactions to the minimum possible.
Sorry, were you done with your question, or do you want to add something?
Oh, I was muted. I was asking the next question muted. I'm sorry.
No.
Yeah.
I did answer I did hear the question about the pairings and everything. Like
I was asking the second one. Sorry, the one about the pairings, it makes complete sense and it's completely clear. But I was asking another question to you after that. But I think I was muted and you didn't hear. Is it okay if I ask it?
Yes, please.
So mainly the thing that I want to understand is related to the statement that you have mentioned about the generation of randomness in random elements, which seems also to be like highly impactful here, not only the fact of reducing the amount of pairings required, but also the amount of random field elements that we need to generate. My question is like how we can envision that more clearly, because I don't see like what prevents you from actually having, I don't know, some selector enabled which allows everything to pass. You only turn up this selector once within the entire circuit, and you put a random witness value there. And then you have kind of blinded everything once you batch and accumulate the entire thing. Or that's at least, maybe that doesn't hold. I haven't checked it, but that's what comes to my mind. So can you give some intuition on why you get such a reduction on the randomness that you need to generate? And also if you foresee any other ways to go that way?
Okay, so perhaps through, yeah, if you, so I'm just trying to reformulate your question to make sure I understand it correctly.
Sure, thank you.
So essentially, to achieve a zero knowledge property, you want to place a random witness value. Basically, you want to have like an extra row in Plonk arithmetization when you place a random value, basically randomize everything. Even if you do that, you know, this would probably help you when you commit to your wire values. But you then have no guarantee that you, by the way, first you need to do something slightly different, but it would be in that direction. But even if you were to do that, you have no guarantee that your evaluation proofs afterwards don't leak more than just the claim evaluation.
Can you expand on that?
So when you do sum check, you know, at the end you have your evaluation proofs.
Sure.
Yeah. So if you want your entire protocol to be zero knowledge, you know, first you need a zero knowledge version of sum check to make sure you're not leaking information about wire values. But at the very end, since the verifier is not the one doing the evaluations and the verifier only has commitments to wire values, you want to make sure that your evaluation protocol itself is zero knowledge as well. So basically, you need that every bit in your every component is zero knowledge.
Yeah.
So in particular, you want that your evaluation protocol for your multilinear scheme is zero knowledge as well. If you want the entire protocol, the entire arithmetic satisfiability circuit to be zero knowledge, provably.
Makes sense. Thank you.
So yeah, and perhaps something was a bit confusing about the pairing. So I would say, you know, multilinear KZG already gave you, you know, the answer for multilinear evaluations with log n pairings. If you optimize Gemini, you actually get a constant number of pairings. I think it's like 3 or something pairing computations. So, you know, like Tohru said at the beginning, the main motivation was actually not yet the pairings, the number of pairings you would have to do, but rather, you know, you wanted to reduce the amount of randomness as much as possible without sacrificing the already constant number of pairings that we had with Gemini.
Makes sense. Thank you. Are there any other questions from anyone? I'll assume not. And I don't see anything in the chat either. So yeah, thank you very much, Tohru, for giving the talk, and also Patrick for being here and providing some additional support and answers to all of the questions. Congratulations on your work, guys, and thank you very much for being here today, sharing your knowledge with all of us. I appreciate it so much.
Thank you. Thank you very much.
Take care. Have a nice day.
Take care.